Howdy. I'd like to share with you today a powerful theorem that will allow us to compute limits that would be otherwise unable to be computed because they simply don't fit into our limit properties or alias theorem framework very well. And that theorem is sometimes called the squeeze theorem. Because our function, whose limit we are trying to find, is going to be squeezed between an upper bound and a lower bound. Your book calls it the sandwich theorem. But I can't quite bring myself to consistently use that term, so you'll hear me use both of these terms to refer to the exact same theorem. And here it is. It's pretty straightforward. Suppose we have three functions. Our function f of x is going to be squeezed between an upper bounding function called h of x and a lower bounding function g of x. So if f is bounded above by h, and it is bounded below by g, and if we are so fortunate that the limit as x goes to c of g and the limit as x goes to c of h happen to be the same value, then it must be the case that the middle function is squeezed to the same limit. If these two things are true, then the limit as x goes to c of f of x must be L also. Well, let me show you, first of all, a picture to justify why this is true, and then I'll show you how it's used in practice. So our picture is this. We have some function, f of x. In fact, I'll go ahead and give you an f of x that this might apply to. Let's let f of x be the function sine of x divided by x. And I want you to observe that if I try to find the limit as x goes to 0 of sine x divided by x, then my form is 0 over 0. But because sine of x is not a polynomial, then it's not at all clear how I would factor anything out in order to cancel. So I cannot use cancellation technique on this. I can't use rationalization technique on this. I cannot use any of the limit properties because the denominator goes to 0. I am stuck. What we'll talk about in class tomorrow, what I'll prove in class tomorrow, is that it just so happens that sine of x over x happens to be less than or equal to 1 over cosine of x. And it also happens to be greater than or equal to cosine of x for all x. Take a moment to graph these three functions on the graphing calculator to verify that what I'm telling you is true. You should be able to see that 1 over cosine x comes down like this, and cosine of x comes up like this. So that sine of x over x, our middle function, is squeezed or trapped between these two functions. And now for the squeeze theorem magic. If I take the limit as x goes to 0 of the two outer functions, then both of these are easily evaluated because cosine is a nice continuous function and cosine of 0 is equal to 1. In case you forgot that, check your unit circle. And so these two limits are the same value, 1, here and here, and therefore I can conclude that the limit as x goes to 0 of sine x over x must be equal to 1 also. Now tomorrow we'll talk about how I came up with these two inequalities to begin with. But what I want you to see is that we met the conditions. We found a lower bound and an upper bound that both went to 1 at 0, and therefore sine x over x is forced to go to 1 at 0 also. Let me do one more example that's more abstract. Suppose I have a function, and I don't know anything about it except that it satisfies the inequality f of x is trapped between 4 minus x squared and 4 plus x squared for all x. And then I have a question. What is the limit as x goes to 0 of f of x? Well, seeing that f of x is trapped between a lower bound and an upper bound, I ask myself, I wonder what do the lower bound and upper bound go to when x goes to 0? And lo and behold, when I check that, both the lower bound and the upper bound both go to the same value, which is 4. And because of that, the middle function must also go to 4 as well. And that's my conclusion. So the picture that we have is that I have some weirdo function f that I don't know about. And maybe it has a hole in the graph and maybe it doesn't. But that weirdo function is trapped between 4 minus x squared and 4 plus x squared. And both 4 minus x squared and 4 plus x squared both go to 4 right here when x goes to 0, which squeezes or forces f of x to go to 4 as well. So that's the spirit of the squeeze theorem. Now, you may ask yourself, how did I find this out to begin with? How did I find these bounding functions to begin with? And the good news for you is that you will almost never have to find these bounding functions for yourself at this level. Later on in Calc 2, we will do some examples where we have to find some bounding functions. And I'll show you some instances in class where we can find bounding functions easily. But usually, you're just given the bounding functions, and given those bounding functions, you check the limits of those bounding functions, and if lo and behold they both go to the same value, then voila, your middle function must go to that value as well, because that is the statement of the squeeze theorem, which I will restate as we say goodbye. If f of x is trapped between h and g, and the limit as x goes to c of g is the same as the limit as x goes to c of h, which has the value L, then it must be the case that the middle function goes to L as well.